And this is work that I did with Ilya, Sergey at UCL and my advisor Zach at the University of Washington. So today I'm going to tell you about programming and proving with distributed protocols in the distributed separation logic called Diesel. So distributed systems are a pervasive part of modern infrastructure. In these talks we're asking questions using distributed systems. The video is going out over a live stream that's on a distributed system, and we really use them all over the place. And the way these systems are typically built is by composing distributed infrastructure with some sort of application logic. So there's all kinds of platforms that you can use to build your distributed systems, and they do a lot of the hard work for you. And then you take your application logic and you can build your favorite social media platform on top of it. And because of the pervasiveness of these pieces of infrastructure, the research community has looked into verifying distributed systems for a long time. And some exciting results recently have looked at verifying implementations of distributed systems. So if we want to imagine a world where we're actually verifying our distributed systems, how is that going to look like given this split between verified distributed infrastructure and application logic? Well, we could imagine a world where we have that verified infrastructure, and then we would think, we just take it off the shelf and build our verified application on top of it, okay? But this is really not the way contemporary techniques work in verified distributed systems. And so the sort of straw man approach that I'm going to stand up here is that I claim you would basically have to start over from scratch if you wanted to build a verified application while trying to use some verified infrastructure such as a consensus protocol. Okay, so this is unacceptable, and it indicates some deeper problems with the way these verification systems work in the sense that they're non-compositional. So I want to identify 3 challenges in compositional distributed system verification, which I'll talk about for the rest of the talk and talk about how Diesel solves them. So the first challenge is client reasoning, which is essentially this idea that typically you have your infrastructure running on some servers and your clients are running on different nodes. And if you want to verify the client application logic as well, then the verification framework should support that. There's also client-specific reasoning that goes into proving invariants. So typically the infrastructure will give you some guarantee about its core correctness, and you want to use that to prove that your application logic is also correct. So how do you add application-specific invariants to the verification framework? And finally, I want to talk about separation, which is really about how do you compose multiple pieces of distributed infrastructure together to build complex applications. So in the rest of the talk, I'll tell you about Diesel, which is a distributed separation logic that solves these challenges using ideas from separation logic. So I'll introduce you to what we call protocols, which are basically an interface between different nodes interacting in a distributed system. And then I'll tell you about a couple of logical innovations that we've made to support compositional verification. Okay, so I'm going to start by showing you how protocols work through a running example. And then I'll move on to showing some of those logical mechanisms I mentioned, and I'll summarize with how we implemented Diesel. Okay, so the running example I'm going to use for the rest of the talk is what I'm somewhat optimistically calling cloud computing, which is really just a toy example doing integer factorization. So imagine a client-server infrastructure where the client sends an integer to the server that it wants to receive the factors for. Okay, and let's imagine we want to build this very interesting and sophisticated distributed system in a verified fashion. Okay, so contemporary techniques are going to tell you to focus on the server and to look at how it's implemented and focus your verification effort there. So let's look at a simple implementation of a server. It's going to sit there in a loop, waiting for some client to send it a request. It's going to compute the factors of that integer locally, and then it's going to send a response back to that request. So this is a very naive and simple implementation. So how do we specify and verify this server? Well, typically what you would do is you would say that all the messages that the server sends back to the clients have correct factors corresponding to the requests that they were given. Okay, and the way you prove this typically is just by finding an inductive invariant. So why is this not sufficient? Well, I encourage you to look at the client. So when doing the verification in sort of the contemporary style, what happens is you focus on the server, you basically treat the entire system as if the client was external. Okay, and so that inductive invariant you found doesn't actually say anything about the client interaction. So if we look at a client, it's going to send a request to the server and wait for a response and maybe make some assertion that the factors are correct. And this inductive invariant that I showed you on the previous slide is really only about the server. So what should we do if we want to build this verified application? Well, I don't want to start over. So what we're going to do instead is phrase our verification in terms of a protocol that describes an interface between the client and the server, so that we can take our verification results that really used to apply only to the server and use them to verify our client logic. Okay, so protocols encourage you to zoom out from just the server and incorporate basically your whole system and to describe the interface between the nodes in the protocol. And this is what gives us our compositional verification. Okay, so what does a protocol look like in general? I'm going to show you the different components of a protocol and then how to fill out the protocol for this simple integer factorization example. So a protocol contains both the set of messages that the nodes exchange. It contains the local state, the local abstract state of each node, and it also describes the various transitions of the system. And by transitions, I'm including both allowable message sends and allowable message receives. So when I describe what kind of message transitions can happen, the two possibilities are either I tell you you're allowed to send a certain message subject to a certain precondition, and that may have effect on the abstract state. And similarly, when you receive a message, you may also change the abstract state. So I'll show you what this means in more detail by filling it out for this integer factorization example. So the messages are just two messages: request that some integer be factored and a response containing the set of factors. The abstract state is really only present on the server, and it contains the set of outstanding messages that the server has received but not yet responded to. And then there are going to be 4 transitions corresponding to sending and receiving each of these messages. And each of these transitions may have some effect or precondition. So the first transition is the one for sending a request, and it has neither an effect nor a precondition. In other words, at any time, a client is allowed to send a request message to the server. When that request reaches the server is going to add it to the set of outstanding messages that it has. So that's the side effect of the receive transition for the request message. And then when the server decides to respond to a message, first of all, it must do so to a message that it has already received. So we require that the request is in the set of outstanding messages. And it computes the factors locally. And the precondition for sending a response is that you have correctly computed the factors. And as a side effect, it removes the request that it's responding to from the set of outstanding requests. Okay, and finally, there's another trivial transition for when the client receives the response from the server. All right, so those are just a basic protocol with 4 transitions, and that's going to be our description of this integer factorization example. Okay, so that's just a brief introduction to protocols. And I now want to show you a bunch of different programs that we can write in this protocol that exercise various logical mechanisms in Diesel. Okay, so let's go back to the server that we had. It's a very simple implementation of the server. And look at what verification of the server looks like in Diesel. So we're going to do, Diesel is based on Hoare type theory. You might think of it as a distributed Hoare type theory. So our verification is going to consist of using Hoare-style rules to reason about this implementation. So the sort of most interesting aspects of that Hoare type theory are the message sends and receives. So I mentioned in the transition for sending a response that the server will be required to show that it correctly factors the integers. And I want to show you how that shows up in a cartoon version of this Hoare logic rule for sending a message. So imagine we're in the middle of our proof. We're trying to verify this implementation, and we get down to the sending of a message. And in each case, we're going to label the send command with the transition that it corresponds to in the protocol, and we will require that that be a valid transition from the protocol. So this is what enforces that you can't send messages that are not described in the protocol. And each transition has a precondition, and that will be the precondition that we put into the Hoare rule for send. And in the post condition, we're going to, I'm going to sort of hide some details here, but the basic idea is that the post condition of a send command tells you that the message has been sent and that the side effect has occurred on the local node. Okay, so given this rule, we can apply it to our implementation and show that this server correctly factors integers. Okay, so where contemporary techniques broke down was in the client, so let's go back to the client and look at what happens. So similarly, imagine that we're trying to do a Hoare-style proof of this client's correctness. And we get down to the assert statement, and we want to know what in our context is going to guarantee that, that the factors are correct. Well, although the send transition of the server required that the factors be correct upon sending, there's nothing in the receive transition that tells you that. So when we set up this protocol, we put a requirement on the server, but we didn't propagate it through the network to the client. Now, you might think that that's just a mistake and we could go back and reformulate our protocol to do that, and that is a valid approach, but I want to show you a different way of doing it just to illustrate another technique that we have in Diesel. So another way to do this is to add an invariant to the protocol that allows you to get an additional postcondition in any command. So this is a rule that we call the with-inv rule that given any program in some protocol and a proof that some invariant I is an inductive invariant of that protocol, you are basically allowed to add I to any existing proof. So in the case of the cloud compute example, what this means is we can go to our protocol, we can enumerate the transitions, and show that no incorrect factors can ever be present in the network. That's an easy inductive proof because it's required at each send at the server. And then we can use that fact to fix our proof of the client. So with this new protocol that contains a new invariant, the receive transition will now allow us to prove this assertion that the factors are correct. Okay, so that's one logical mechanism, the with-inv rule. So another mechanism is analogous to a sort of frame rule in separation logic. So imagine a slightly more complex client that communicates with multiple servers, both via the same protocol. And it has a similar assertion that is, makes some true assertion about the factors of 21 and 35. And the same protocol enables the client to do this because of our analog of the frame rule. So this cartoon version of the frame rule basically allows you to inject a smaller protocol and proof into a larger system. So in the example I was just showing you, the fact that there are two calculator nodes is easy to express with the frame rule. Okay, and the one nice thing about this is that even though you're changing the protocol by injecting it into a larger system, you get to reuse any invariants that you've proved about the smaller protocol. Okay, so that's the basic idea of the frame rule. One interesting thing that probably doesn't show up in other separation logics is that we have this problem where often in distributed systems, your components are not independent. And as I've presented this rule on the slide here, I want to emphasize that it requires the protocols to basically have nothing to do with each other. So it makes it easy to take completely unrelated things and put them together, but it doesn't give you any way of building sophisticated interactions between protocols. So we've introduced a logical mechanism that we call hooks to facilitate this kind of sophisticated composition that allow protocols to restrict the actions of each other. So in slightly more detail, what happens is that when you compose two protocols using a hook, you can add a precondition to an existing transition. So you can say that this transition from a separate protocol, well, it used to have that precondition, and now it has this additional precondition that can refer to state in a different protocol. Okay, and this lets you decompose applications that would be challenging to decompose otherwise. Okay, so that was just a brief overview of three of the logical mechanisms that Diesel has to offer supporting compositional verification. And now I want to look at how we implemented this. So we implemented Diesel as a shallowly embedded programming language in Coq, sort of in the style of FCSL, if you're familiar with that. And this leads to several advantages. First of all, we don't have to repeat ourselves and introduce a bunch of functional programming primitives that are already present in Coq. We can reuse existing list libraries and so on are easy to use in a shallow embedding like this. Another advantage is that it's easy to support executable code via extraction to OCaml. So because we're a shallow embedding, we can use Coq's existing extraction mechanism to actually generate OCaml code that's implementable. And of course, one caveat here is that all of the impure features of our language need to be explained to the extraction system what to do with them in OCaml. Right? So sending and receiving are not pure operations, and we need to map them to some impure operations in OCaml. And we have a shim that does that executes them on via the operating system on the real network. Okay. And the paper also describes a larger case study from databases where we implemented a two-phase commit protocol, and we exercised several of the features of the logic that I mentioned earlier in the talk, including adding invariants to the protocol, and a hooking protocol that allows clients to read elements of the database. Okay, so in related work, I think it's best to think about this project sort of at the intersection of both the field of concurrent separation logic and verified distributed systems. There's been a lot of work on verifying distributed systems. There's been maybe even more work on shared memory concurrency separation logics. And so one of our goals was to port some of those ideas into distributed systems. So things that are related are things like Verity, Ironfleet, Chapar, EventML, on the verified distributed system side, and then on the concurrent separation logic side, things like Iris, FCSL, abstract predicates, and so on. In future work, one thing that I'm interested in looking into is how to add effects other than distribution to this logic. So Diesel right now basically gives the ability to reason about protocols separately and how they exchange messages, but each node's local execution is very simple. It doesn't support, for example, a mutable heap or local concurrency in the form of threads. So I think it would be interesting to look into how do we essentially stack program logics or stack verification where we have local concurrency as well as distribution in a way that doesn't require sort of considering those at the same time. Okay, so I thought I would close with a quote from Leslie Lamport. I think this is the second time Leslie's face has appeared on a slide in this session. And I'll just read this quote to you. He's writing in 1997, and he says, "The unfortunate reality is that engineers rarely specify and reason formally about systems they build. It seems unlikely that reasoning about the composition of open system specifications will be a practical concern in the next 15 years. So Leslie Lamport thinks that compositional verification is unlikely to be relevant. Well, in some sense, he was right, because he was writing more than 15 years ago. So in the 15 years since 1997, people didn't really look at specifying distributed systems compositionally. The other thing that I think is that has changed since then is that it's now the case that it is sort of typical to reason about and verify implementations. And in 1997, that would not have been typical. So I think we're at a point now where it's time to look again at compositional reasoning and apply it to the various application domains where verification is becoming popular. Okay, so just to wrap up, I sort of told you about verified distributed systems and 3 problems in compositional reasoning, in building applications on top of infrastructure, in adding client-specific invariants, and in composing sophisticated systems out of simpler parts. And I told you about Diesel, which is our distributed separation logic that uses some novel logical mechanisms to address these challenges. Thanks, and I'll be happy to take any questions.
So in your within rule, you referred to a kind of invariant that you called inductive.
Yeah.
Is it related in some way to the kind of invariant that Derek Dreyer yesterday called persistent?
Is it related to a persistent invariant from something like Derek's Iris logic?
What is an inductive invariant? I guess
Right.
I didn't make that clear.
So when I described a protocol, I described it as basically a set of transitions over some state space. And so if you think of that as a state transition system, then what I mean by inductive is that it's an inductive invariant of that state transition system.
Preserved by transitions in that.
Exactly.
So that does seem a little bit like what Derek called
Right.
persistent.
I have a different question.
Sure.
So is there something fundamentally new here compared to FCSL in terms of logical mechanisms, or is it just a new application domain?
So certainly there is a new application domain. So both the with-inv rule and hooks are not present in FCSL. And so those are the novel logical mechanisms.
Okay, but the hooks seems somehow related to the entanglement operator in FCSL.
They are related to an entanglement operator from FCSL. I think probably we should take an in-depth discussion of that offline.
Okay, but it's something beyond the entanglement.
It is something beyond the entanglement, yeah.
I also have a question about the with-inv rule. Can you show that one
Yeah.
once more?
Just.
So I'm a bit confused about this, because usually these invariant rules, they are upside down, unless I'm sleeping. Because usually it means that whenever you want to prove a hot triple, PCQ, then it suffices to prove that under the assumption of having I in the precondition and the postcondition. But here it seems to be the premise and the conclusion. Why are they this way? Why aren't they swapped?
Yeah. So this
the
is
invariant rule in Iris, for example, there it's upside down.
right. So in this version of the rule, what I'm saying below the line is essentially that for free, you can assume that the abstract state satisfies the invariant I. Right. So every state that shows up during an execution of the system satisfies the invariant I. So it's as if it's true in both the pre and post state.
But in which way can you assume it? Because you have to establish it whenever you want to use this hot triple.
Right. So the way I've written it on the slide here, the precondition it looks like it requires you to prove I. In fact, you will not have to do that because every state in this primed protocol satisfies I for free.
Okay. We probably should take this offline because I don't understand it.
Okay. Thanks.
So session types have been developed in order to describe the kind of communication protocol that were in your example. And it leads to a notion where everything is much purer in some sense because you have some kind of linear logic on one side and you have a functional programming language on the other side. So have you considered using that? And if so, what is the showstopper for using them here?
So definitely we are related to session types, and they do describe communication interfaces in a similar way to our protocols. I think one thing that I think we find it easier to do in this style is sort of functional correctness verification with arbitrary application logic. So because we're embedded inside of a proof assistant like Coq, it's easy to bring in any verification libraries about the application domain that might be relevant. And those are trickier to incorporate with session type style verification.
Well, I think I would disagree on that because maybe the current state of the verifiers is not there.
Right.
But on the other hand, it's a much purer approach. You don't have to model local state and state transitions because they're built directly into the logic.
Right. Yeah, I think it's an interesting avenue for future work, for sure. Thanks.
We have an online question which basically asks if you can express and verify your protocols using Ivy.
Using what?
I think it's Ivy.
Using Ivy.
Yeah.
Huh, I wonder who asked that. Yes. So certainly, I think the protocol is, like I mentioned in an answer to an earlier question, is basically a state transition system. So insofar as Ivy is able to reason about those things and embed them in first-order logic, then it would be relevant and could be useful, for example, for discovering strengthenings of properties that you wanted to prove inductive.
Okay, let's thank our speaker again. So this is the end of this session.